Welcome everyone. I am Dr. Arpita Datta. I work as a research fellow at National University of Singapore. But the work that we are going to discuss today, EBFL, an ensemble classifier-based fault localization, is I have done at Indian Institute of Technology, Kharagpur. So now we are going to start the presentation. As we all know that with the increase in size and complexity of software systems, bugs are completely inevitable. And whenever a software developer faces any bug in the program, the first thing he tries to do is to localize the bug. And for localizing a bug, a number of automated bug localization techniques are already available in the market. And the input for those available techniques are somewhat like statement coverage information, sometimes the history of the buggy program, complexity metrics related to different program elements present in the program, execution result of test cases, and many other information. So, by collecting all this information, this automatic bug localization techniques, what they do, they generate a ranked list of statements based on their priority of containing a bug. Like these techniques, but the problem with these techniques are that is they are not effective and efficient enough. Oftenly we see that these techniques require examination of huge number of statements to reach to the buggy line. Therefore, we thought to propose an effective fault localization technique, because we know that even if we will be able to reduce a little bit in the software development cost, we will be able to reduce the whole software development time up to a large extent. Now, coming to the different available techniques for fault localization, we are going to understand some of the available techniques, because in our proposed method, ensemble based classifier, we have used already established fault localization techniques and then we have combined those. We will also going to see that why we have combined the existing techniques and all. So basically, I am classifying the existing fault localization techniques into 5 families. So, like 5 families like slicing based, spectrum based, neural network based, mutation based, and the other techniques like data mining and all. I'm keeping them in the 5th category known as miscellaneous. So, the first category is the slicing based. Different slicing based techniques are available like dynamic slicing, hybrid slicing, static slicing. Actually, the initial fault localization techniques which I propose are slicing based only. But the problem with these techniques are that oftenly they return a large chunk of program statements to the developer to examine for bug and without any ranking. So again, it leads to a confusion state for the programmer. Therefore, people move from the slicing based techniques to other techniques like spectrum based. Spectrum based is another established fault localization family, and these techniques, what they use lightweight information, only the statement coverage result and the text execution information, that whether the test case is passed or failed. And using this information and some mathematical formulas, they compute the suspiciousness value of each of the program statement, and then they rank the statement based upon the suspiciousness value of this statement. For example, some of the established fault localization, SBFL fault localization techniques are Tantla, Okai, D star. And the formulas for these techniques are this, like we have mentioned here, and the variables used in these formulas are like NP. NP shows the number of past test cases present, number of failed test cases, and EP shows the number of past test cases that have invoked the statement S, and the number of failed test cases that have invoked the statement S. So these are the variables that we will get from the statement coverage and text execution result. And based upon these values, they generate the suspiciousness score of each of the statement. And then, but the problem with these techniques is that they assign same rankings to the multiple statements and all. So people have moved and people have proposed other technique like mutation based technique. So in the mutation based technique, instead of taking test case failure as success result, mutant kill and alive information is taken. The mutant kill and alive, the first thing is mutant. The mutant is one version of a program with minor change, with some changes. So at present, we have considered only single fault mutants. Single fault mutants means we have to make only one change in the mutant generated for a program. So then they have mapped the kill and alive the number of pass and fail test cases to the kill and alive information, and uses the same formulas as in SBFL in the MBFL to generate the suspiciousness value of a statement. And then finally they generate a ranked list of a statement. But this technique doesn't perform well when all the test cases, when all the mutants are killed by all the test cases, and also they are sometimes computationally expensive. So the other category of fault localization techniques that is neural network is came into force. So as we all know that like in every field of software engineering and other fields, neural network plays very well and solves many problems. So here, first the Wong et al. Used BP neural network, backpropagation neural network, to solve the problem of fault localization. But the BP neural network, even though it is easy to implement and execute, it suffers with the problem of local minima and paralysis. So people have moved towards radial basis neural network, and further other improvement have been done, that is deep neural network, convolution neural network, and recurrent neural network are also proposed for fault localization. These are the different families of neural networks. Like the convolution neural network is able to handle large size of programs by downsampling and the distributed weighted program, and recurrent neural network have a policy to remember the previously executed or previously computed values. So they perform really well for the large size programs. And then uh, like these are the different techniques that are available other than the data mining and formal methods that are used. We are so now we will discuss our proposed method, that is EBFL, that why we have proposed this method. Okay, and how we have utilized the existing techniques. So basically we know that there is no single fault localization technique which perform effectively or which outperform than other methods for each and every type of program. For example, some of the methods perform very well for arithmetic works, and other perform very well for the global variable works. But to capture or to use the effectiveness or the benefit of each of the technique, we try to combine their effectiveness. So we know that Ensemble classifier agglomerates the best of each of the base classifiers and performs better than all its base classifiers. So based upon this funda, we have used Ensemble classifier, and for that we have taken three fault localization families in account, which are SBFL, MBFL, and NNBFL, like spectrum based, mutation based, and neural network based. So, and from these families, we have taken the state of art methods, and in combined, we have 11 methods. So, from SBFL technique, we have used Templar. This is a classic method, and the funda behind Templar is that Templar works like the statements which are frequently executed by the failed test cases has more susceptibility of containing a bug than the statements which are more executed by more number of times executed by a past test case. Now the Okai is a biological theory inspired method, but like unlike the other techniques which doesn't use the information of the number of failed test cases which have not executed a particular statement, is also be used by the Okai to decide their suspiciousness score. And the last is the method we have used is D star is a state of art method, and it performs really well than the other existing SBFL techniques. Now, to make a consistency, we have taken this method only for MBFL also. And in NNBFL, we have used BPNN, RBFN, DNN, and CNN and RNN. So, initially, we computed the suspiciousness value for the statement by each of this technique, and then we have generated a we have done a voting to classify the statement in two categories like suspicious statement or non-suspicious statement. So our voting scheme works like this, like if any statement is more than the median of the value of suspiciousness score for the whole for all the statements for more than 6 number of these false localization techniques, then it can be classified in a suspicious class. Otherwise, it is classified in the non-suspicious category. And then we will examine only the statements that are present in the suspicious class. So, for the suspicious statements, we have done the score normalization. Actually, the scores generated by different techniques are in different range. So, to make a proper before making a combination of this score, we have done the score normalization by dividing the score of a statement by the total of the scores of all the statements. So it normalizes the score of all the statements between 0 to 1. And then we have used learning to rank method to combine the score of each of the to combine the score of the all 11 methods and generate a final rank list of suspicious statements. So, and then this is our method, and then we have also experimented with some programs to see the effectiveness, so to check its performance. So we have done the experiment on 64 GB RAM system, and tool that we have used to generate the coverage information is Recurve, and the data sets that we have used are Siemens Suits, Space, gzip, which are downloaded from SIA repository. The fourth set we have downloaded from NTS repository, and the last is the DefectJet. And we have seen the relative performance of this method, and we have compared it with Tantler, D-star, DNN, CNN, and RNN. Also, we have made comparison of the values with the average, best, and worst case of Tantler, D-star, BPNN, RBFN, DNN with contextual information, and we see that our method performs really well both in the top 1% and top 5%. Like by examining on a top percent how many how many buggy versions are getting localized. So we see that the quite a good number of versions are localized by our method. We can see in the last row, and then last row, and overall our method is 58% more effective in terms of less code examination than the existing related FL techniques. Now coming to the runtime, actually the runtime of our method is more because we are using 11 different methods. That is the problem. That is one of the like limitations of limitation of our technique, that it requires huge time. But we are getting a good performance. We are getting good results, so we can compromise with that at this moment. And in future, we will try to reduce the this time, and also we will work for the multiple fault programs. These are some of the references that we have used. Thank you so much.